for our seminars. And first one is Griffin-Pickering from Durham, and she's going to talk about mean-field games and control and acceleration.
Thank you very much. Thanks to all of you for bearing with me during the technical difficulties. Especially thanks to the organisers for the really kind invitation to speak today. It's very nice to be back in Cambridge. So what I wanted to talk about today was a recent project. It's a collaboration with Alp&aacute, who's a colleague from Durham University. And he works in mean-field games. And so the question kind of, how does this connect with the theme of this program might not be immediately apparent, but I hope to get that across within a few slides. Essentially, we looked at a class of mean-field games that have some kind of kinetic structure. I want to start off by introducing what mean-field games are and just the various notions for experience. So the theory of mean-field games goes back to the work of, goes back to about 2006 when it was introduced by two teams, Basri Newells and Keynes, kind of engineering control perspective. And the purpose of this theory is to describe a population of a large number of agents. Agents kind of suggest that they have some choice about their dynamics. And they're interacting with each other by being players in a game in the sense of mathematical game theory. The kind of mean field name is born to get an analogy with mean field vector particle systems. So the idea is that you're thinking of these players as being indistinguishable and small in the sense that the effect of any one individual in the game is negligible, but as a collective, they can influence each other. And so the applications of this theory come from areas like economics, collective behaviour, and finance, various kind of settings from social sciences and biology, where the dynamics of these individuals have some element of choice. So I'll talk a little bit about what a differential game is specifically in the next slide. First, I just want to set up the idea of a mathematical game. So kind of in a simplest expression of a mathematical game, we're thinking of something like the prisoner's dilemma or game of rock, paper, scissors. So each of your players is given a state space from which they can choose their state. And then once everyone's chosen their state, they receive a payoff, which depends on the state that you choose and also the state that everybody else chooses. And so the mean field part of the setting.
You go to the 3 points, you can change the view.
3 points.
Yes, there. Same thing. Change.
Just a connected.
Yes, that one. Okay.
So you put it in the least useful corner. No, maybe the page.
The left one. The left one.
Thank you.
If it's not,
Yeah.
Wonderful. Thanks very much. So where were we? I was talking about, so you have some kind of payoff that's incentivizing your actions, and it depends on the other players in the population. So in the mean field setting, as I said, the effect of any individual is negligible. Instead, you feel the influence of the other players through as a collective, described through a density function, which I'll call M. This is something familiar for those of you familiar with kinetic theory. And so, the payoff function for an individual player, say a typical player, is going to depend on their own state and also the density of the other players over the space of states. Okay, so a differential game is a particular kind of mathematical game. In a differential game is played in continuous time over some interval time 0t. And the player's state is the trajectory in the state space over that interval of time. And the dynamics of that state are described by a certain control ODE, which is the dynamics are given by some function b. And you can see that this looks like a regular ODE up to the inclusion of this parameter alpha. Alpha is a control parameter that the player is going to be free to choose. So if this looks okay, for the purposes of this talk, I'm essentially going to talk about two key examples. The first one is the case most commonly studied for game theory, where the control is exactly equal to the time derivative of the state variable. I'm going to refer to this as the control velocity setting, which isn't standard terminology, but I'm using that name to compare it to the second system that I'll discuss. So the control velocity name comes from interpreting this as a kind of system of mechanics. X is the position variable and alpha is the velocity. The second system is the main one, the main point of this talk. Instead of the first system, you look at a system in which alpha gives you the second derivative. So you can think of this as a choice of acceleration. You could imagine that you're choosing a force to apply. And this is expressed as a phase space, X and B. Yeah, and so mean field games based around the second system are going to be the distance. So this is the first part of the rules of the game. This describes how a player is able to interact with their state and influence how it happens. The second part of the rules of the game are what the players are trying to do, how they interact with each other, and that's through their attempt to optimize some payoff, which I've phrased here as minimizing a cost function. And so this takes this form that's rather common in differential game theory. There's a part of the cost that's called the running cost, which is picked up over the time. There's a typo on the slide that T0 should be 0 in this case. So that's the cost that you pick up over the course of the game. And then there's a terminal cost term, which is the cost that's based on just where you end up at the end of the evolution. And both of these, as I discussed, are going to depend on all of the other players through their density MT, density of excellence. But of course, how that density evolves is going to depend on the strategy that the players choose. So if the players are playing according to the choice of control alpha, then the density M should satisfy the continuity equation you see in the slide. So that has the characteristic system, which is the control I showed you. So then the question is, how are players going to choose their strategy? And for this, we refer to a notion from game theory, which is the idea of a Nash equilibrium. So a Nash equilibrium is a kind of notion of optimal strategy. So alpha star is a Nash equilibrium if, given that you know that everybody else in the population is going to play alpha star, then alpha star is the optimal control that you could choose. If you choose something else, you can't do better. So this is the kind of solution of the game that mean field games is trying to represent. The next question is, how can we find such an optimal strategy? By what means can we find a strategy that's an optimal response to some evolution of the density? And if we can solve that problem, then our Nash equilibrium would be a kind of fixed point fix. So for this, we're appealing to some notions from optimal control theory. So optimal control theory is about optimally controlling RGs to optimize some functional, which is exactly the setting we have here. And there's an important notion in this theory, which is called the value function. So what the value function does, so we're going to find this in life. Let's not bother.
It would work. It would work.
Okay, and this diagram's not too important, but let's say I've got state space along here, and here. So the value function is saying, let's say that you know that your player is state Z at time t, at some point. You're going to evolve up until the end of the interval in some way. The value function says, along the remaining time left to you, what's the optimum cost that you could incur over this length? Okay. And the key fact from optimal control theory is that at least formally this value function solves a PDE, which is called the Hamilton-Jacobi-Bellman equation. So you can see it's a Hamilton-Jacobi equation where the Hamiltonian H tilde here has a particular dependence on the state dynamics B and the part of the running cost function from before that depends on the control. If you have the value function, this also gives you a way to find your optimal control because it's related to your optimal control is related to the value function through this relation to B and the derivative. Okay. So if you put all these notions together, we find that this mean field gain problem we were talking about is represented by a system of PDEs. So what we do is we take the Hamilton-Jacobi-Bellman equation and you couple it with the continuity equation that explains how this player's the density of player states evolves if they play according to this optimal strategy. So that's how you get the two systems that you see. And I've shown the mean field gain system in the two cases that I described. So in the first case, kind of more typical case in the theory, with control on the velocity, you get the first system, and you can see some key features. This is a forward and backward system because the Hamilton-Jacobi equation is a terminal value problem, and the continuity equation is an initial value problem, and they're coupled to each other through the dependence of the right-hand side of the HJB equation M, and in the continuity equation, the optimal strategy depends on B. Okay, so the system that I'm going to be interested in is the second one, and you can see that if you replace if you change the ODE for the state, you get a mean field gain system that looks similar to the first one, but with some kind of kinetic structure. So it kind of looks like a kinetic mean field gain system. So the key points are highlighted, so the kinetic transport operator, and also the fact that H here, so this kind of conjugate of L, depends on U through its derivative, but only the V derivative, and that's going to be important later. So, yeah. So the work that I want to present is based on investigating the well-posedness of this kinetic mean field gain system. The theory of mean field games has been had a lot of interest for a number of years now. For the velocity control case, there are by now kind of a large number of works looking at different cases of these systems, whether you include noise, common noise, or no noise with some structural features. There are many works which I won't attempt to summarize here. For the control acceleration case, there are comparatively few. And I just wanted to point out kind of the features of these models that are important for the well-posedness problem. Kind of two key concerns: whether or not you have noise in the system, and the features of the couplings. So how do these coupling functionals F and G that depend on M, what kind of functionals are they? So the first case that's kind of good in some way is when these couplings are regularizing. So the kind of thing, there's some examples of these papers, and the kind of situation they look at is when functionals F and G say map any probability measure into a C2 function in, let's say, a bounded Lipschitz way. And so a key example of that would be if you take some local dependence where your function is a convolution of a nice smooth function. And so there's several examples of well-posedness results from this setting, fixed point methods, including some state constraints. The other thing that you can do is you can add some noise to the system, which you expect to be smoothing. The interesting thing in the controlled acceleration case is that the operator you get is hyperelliptic, so it's not a parabolic structure, as in the velocity control case. But there's a paper from last year that deals with this case for this model and shows some posedness. And the nice thing is that in that case, you can allow local dependence of the coupling on M. So you have a coupling that's just a function of the density. And this is done for either quadratic type or Lipschitz type Hamiltonians with some technical conditions depending on which case you look at. The setting we wanted to look at still has the local coupling case, but without the noise. And so as you might expect, we're not going to be able to prove well-posedness without further conditions in that setting. So what we have to pay is that we look in the case where there's some variation of structure. And this is a setting that's been considered for the velocity control model as well. So it's kind of inspired from a result of Cardelli-Aghier and Graeber, looking at assumptions similar to this on the case of the velocity control system on the tools. So I've given our assumptions on the Hamiltonian couplings here, not in the full generality we could achieve, but just kind of a representative version of what we could deal with. So the Hamiltonian should be continuous and convex different with respect to P, which is our standard assumptions. The important thing is that it should have a power-like growth. So it should look like P is the R, something like greater than 1, up to something at infinity. Then we said we were working with local couplings. So the coupling is some functions F and G applied to M. These should also be continuous and strictly increasing. That's important for the variation problem. And then they also should have some power-like growth. So F like M to the Q minus 1, G like M to the S minus 1. S doesn't have to be equal to Q, but should be less than 2. And finally, on the initial data, we want a continuous bounded probability density with a finite first velocity. What's interesting is that we neither have to take back support or exclude it. We have either case. And under these assumptions, what we show is that there's a weak solution of this weak game system. It's unique in the sense that the density M is unique, and U, the value, is unique on the supportive of M. So if M vanishes, we don't know, but where M is not is greater than 0, in the quadratic case, so if R is equal to 2, we're also able to prove a Sobolev regularity estimate for these weak solutions. I've sort of written it slightly informally as the Sobolev estimates. Really, we get some estimates on some weighted different structures. And for this, we need to take stronger convexity and monotonicity conditions that are technical. I don't want to dive into exactly what this says too much here. So the thing I want to focus on is the well-posedness result. One last thing. Okay, so I told you we have well-posedness for weak solutions, but I didn't tell you what a weak solution was. So the kind of key point is that a weak solution is a solution in the sense of distributions, but where instead of equality, we've got an inequality in the subtractive equation. It should also satisfy an energy inequality, not too much, and some instability conditions, which are essentially just to ensure that the functionals that I write variational properties in a couple of slides make sense always for these weak solutions. But I think that the key point is to point out this inequality. Any question?
It's a quadratic case?
Yes. Which term? If it was, yes, if it was exactly quadratic, yes. Yeah. Okay. Any other questions before I so talk a bit about the proof of this result. It's a variational approach, as I said. So first of all, I just want to describe how this proof works broadly, and then I'll talk about what has to change for the kinetic. So yeah, the overall strategy is that this weak solution, U and M, are each characterized as an optimizer of a certain optimization. This is the approach here. So first of all, the problem for M is defined in the following way. So we take the antiderivatives of our coupling functionals and define functional A, you see on the slide. It was a functional in principle for the density and the control, but actually we changed variables to use this variable W, which is alpha times N, so kind of the force associated to the control, if you like. And yeah, this is the functional that we work with. And we want to minimize this subject to the constraints that M is a possible solution of the controlled unity equation for the control domain. And for U, we have an associated problem defined in this way. So we define the conjugates of the functions calligraphic f and g. Maybe this is something worth recording for those who haven't seen this before. F star, for example. And similar for G star. And then finally, there's another term involving the value density at initial time. And so far, this beta is just a notation for the left-hand side of the Hamilton-Jacobi equation, but kind of that changed a bit. So the first version of this problem we look at is to minimize this functional, let's say, over C1 bounded functions. Okay. The relationship between these two functionals is that, at least formally, they have a duality property, which is what's expressed at the top of the slide. Where does this idea come from? So remember that the minimization problem for A was constrained. If the constraint of the continuity equation should be equal to 0. If you include that constraint in your functional using Lagrange multipliers, which I've spoiler called U, you get the inf-sup problem that you see a little bit further down. And then the idea of this duality is to assume, without justification so far, that you can swap over the order of the sup of the inf with equality. And then if you resolve the Riemann first, formally you find that you have the unity for the sup of minus. Okay. So if you can show that indeed that duality holds, and you have optimizers for these two problems, this tells you that your optimizers are a solution of the meteor game system. Why is that? Well, going back to the argument that we sketched out, if you have optimizers, you're satisfying both the inf-sup and the sup-inf problem, and it tells you, among other things, that M must attain this supremum in the definition of F star for beta, and you read off, because the derivative of calligraphic F is little f, you read off the Hamilton-Jacobi equation. So to actually do this, the key point is to identify some functional spaces in which the duality is actually true, and you have the existence of minimums. So on the one hand, with the spaces I outlined so far, so continuous and bounded for C1 bounded for U, and this L1 space for W, it's possible to use a result from convex analysis, conventional Rockefeller duality, to deduce a form duality and also existence of a minimizer for A. The problem is that we can't then show the existence of minimizer for B within the space C1 bounded. So then you think, let's enlarge the space we minimize over, but the problem is you might lose duality. So we still want to prove both of these properties for the appropriate choice of space. So this motivates the slight modification of the problem. We relax this variational problem. So now beta returns, but this time it's a variable in our function. It's going to be some L1 lock function. And then we also have a gamma, which has a similar property of being an inequality, but for the term vector. So we see these inequalities coming back that we had in the definition. Weak solution, and we're going to minimize this functional over some space, which is essentially designed to make sure that all of the terms in this functional make sense. And we're able to show we're able to show that in fact duality and existence of the minimizer hold for this choice of space. So this is the overall strategy, which is essentially what's done in the paper by and Graeber. The question is, what do we need to add? What's difficult in the kinetic case? What do we need to change? And this all kind of hinges on the analysis of the value function for a value function with the functional B tilde being bounded. We want to get some good estimates on this. To show for the duality, for reasons I might go into, essentially that you can multiply the value of the density together. and also to show for the existence of minimizers that you have some compactness on U when you have bound on beta and gamma. So the first step is to get some kind of basic LP style estimates, sort of thing that's standard for arithmetic transform equation. The problem that you have, so there's an issue here that seems like a technical issue, but is actually significant, which is that in a kinetic case, you have to work on a domain because the velocity must be unbounded. So the problem when you try to do these integrability estimates is you notice we've now got inequality instead of we might be used to having an equality. What that means is telling you that the derivative backwards in time is found from above. So if you're thinking about function, what it tells you is if you have an upper bound here, then it's give you a kind of upper envelope on the function at earlier times. But if you have a lower bound on u at time t, you don't know. But conversely, if you have a lower bound on u at time 0, then that will give you the lower bound for it. So when you have an inequality, you need conditions both at initial and time. That's okay because the function will give us exactly that. But the problem is that the one at initial time is integrated against m0. And that's a problem if m0 vanishes in some regions, as you might want to do if you were going to take impact support or something which might be useful, you think, for the analysis. But it causes a problem, and you can kind of interpret it in terms of the problem as saying, well, what is the meaning of the value if you look at a place where there are no agents to begin with? Okay, so you could think about getting around this by assuming positivity everywhere or a lower bound or something. Positivity everywhere, really you want something like an uniform lower bound, as is done in the case of the torus. But when you're on RD, that's impossible. So we need some way to deal with this. So this is the reason for the introduction of this slightly funny set that you might have spotted in my L1 spaces earlier. So we work on something called the reachable set. This is a notion from control theory. So the reachable set, back to my diagram. So let's say that M0 is positive set, say these ridges. The reachable set is all of the points that I can connect to a point within this positivity set with some choice. There's control that will take me to there. It turns out that for this acceleration controlled system, this is a controllable system. It satisfies the count and route condition, and that tells you that in fact the positive time is everything. You can get anywhere. So the only things we have to exclude are time 0, where M0 vanishes. But the notion we think is kind of interesting as a way to think about it for other systems. And so what we get in this case is we're able to show bounds on U, but locally within this reachable set. Okay. This will come back when I discuss the main point. So the other thing that we need to do is show existence of an enemy. We do this by a direct method. You take a minimizing sequence, you want to show some compactness to extract a limit point. And if you can show lowest limit continuity of the functional, include that your limit point is a minimizer. So the interesting bit for going from velocity control to acceleration control is in the compactness part. So we're looking for compactness for minimizing sequences that are subsolutions of our Hamilton-Jacobi equation, where you've got some LP bounds on beta, which are bound to the balance of the functional. And so the energy estimates I was talking about on the previous slide give you uniform bounds on U locally in L1, and on the V derivative of U locally in LR, or locally so within the reachable set. So if we didn't have any X dependence, if we were just in the velocity control case, this would be enough, because this bit of Sobolev regularity would give us compactness. This is how they conclude in big groups of carbon and paper. In our case, we don't have the same coercivity in the Hamiltonian with respect to dxu. We're missing some estimate there. So we need something to replace this. And so this is where a bit of kinetic theory comes into this problem, and we make use of averaging this. So what is an averaging lemma? So averaging lemmas are results about the kinetic transport equation that tell you if you have some L2 bound of the solution and the source in the equation, there's some additional regularization that it applies to velocity averages. So velocity average, you take some function phi, which is bounded and supported, depending only on v. You integrate your density with respect to phi, and that's what we call velocity average. So kind of classic, one of the early results in this direction is the L2 setting. It tells you that if you GU L2 here, then you get some fractional Sobolev regularity of velocity averages. You can generalize this to the time-dependent equation or general P. You can put derivatives on the right-hand side. You can express the regularity of Bezos spaces, all sorts of things I won't go into. In our case, something that's a little tricky is that we want to treat our Hamilton-Jacobi equation as a kinetic transport equation, so it's on the right-hand side. The estimates I spoke about tell us essentially that the best uniform net bounds we're getting are going to be in L1 opening short set. So we're working with L1 averaging. There's no gain of regularity in that case, but you can still get compacts, which is okay because that's good. So the averaging then we use is from work of Gauss and Raymond, so you need a little bit more boundedness in the L1 case. You need to assume an additional equi-integrability condition in V. And if you have that, then you deduce strong compactness of velocity averages in L1. The equi-integrability condition is okay for us because we have this extra regularity in V.
From where do you get these because we have one? I'm thinking in the quadratic case, and the quadratic case we have gradient Z for choose or in L1. Where it comes down.
So from these, when you do these energy estimates here, basically you it kind of goes back to this diagram. You've got an up and down on UT, a lower bound on U0, and you do some estimates that essentially say you can integrate that and tell you some. So yeah, from this step, you find that you have some integrability. So yeah, we are allowed to do this with integrability estimates, but they're L1. But that's enough to get some strong L1 compactness, but for the averages, we didn't want averages, we wanted the full value function. So the last step is to use a kind of principle that occurs a lot in kinetic theory, particularly as the discussion true on elliptic regularity for kinetic equations. If you use some of these properties of the kinetic transport operator, and you also know that you have a bit of extra regularity in V, then you can introduce some information on the full distribution function. So how we apply this in practice is we look at modifying the distribution function in V only. If you take that convolution and you look at it for fixed V, that is a velocity average. So for each fixed V, you have some compactness. And you have to do a little bit of work using some kind of Ascoli arguments and some of the extra regularity to find that you get, you can extract a subsequence that converges in an L1 sense in V, but you can do it. And then finally, you use this extra regularity to control uniformly in epsilon, or in a way that vanishes in epsilon, the distance between your modified UN and the UN that you're looking for. And in this way, you can pass from compactness of averages to compactness of the full value function. That's the kind of last piece of the adaptation to the kinetic case. So those are kind of the main points I wanted to talk about. Yeah, thanks very much. Very simple. Are there any questions?
In the coupling of the F and the G, there was the assumption that they're both scale like powers, and
Yes.
one of them had to have like power that was less than or equal to the other. Do you go over the intuition?
Yes. So comes in here, I suppose. Maybe it's useful to. Okay, so the powers are telling you, roughly speaking. Yeah, so you've got some. I think I might not remember what I was saying. I don't know. I don't know.
Yeah, it's okay. You can.
Yeah, it doesn't seem. Well, okay, so you can see here the terminal data is in essentially, well, it's bounded by something that's in star. The force in this equation is beta. Plus is in L2 primes, which means that the beta. Well, there's a truncation argument that I'll go into, but you do a lot of truncation, and beta is going to be in L infinity. Prime. And essentially, with this, you can propagate L estimates factors inside value function if you start in the right direction. So you want to start in this way. Yes. It kind of pops out in the middle of an FGS.
Very nice. So your notion of solution is there's a weak solution with inequality.
Yeah.
And you have no deflection, right? No noise.
No, yeah, no noise.
I don't know much about this, but people also look at viscosity solutions for the HCD equation.
Yes.
So these related, like, can you relate the two notions?
It can be related either. So there are some results in. I know there are some results in not this case with the glossary from that show the importance of distribution of viscosity solutions. I honestly haven't thought about it in our case. Something happened in the case. There were some technical results with proving where we were kind of inspired by some results that were making use of this result, and in the end we proved them another way and didn't try to. It's a good point.
Question, the regularity in D comes from which term? I missed that point.
So yeah, so somewhere in this estimate, you've got multiple equation. Like this. This is essentially DU star. And you know you've got some kind of lower bound on zero. You've got some kind of lower bound on U0 and so you can do some energy estimates on this equation when you test it by things from the bound of this, you get a bound stage in the middle, and essentially that will give you eventual
And your estimates to get the regularity in X are probably related, but not the same as hypocoercivity, right?
No, yes, so we don't get regularity in X in the end. You deduce flatness through the L1 averaging, but it isn't actually regularity.
Not even BMO or something like that. No
I didn't think about that.
Okay.
So it's a question, but just as the equation that you have there, I mean,
Yes.
let's write there some equation. Let's write it with a quadratic.
Yes.
function. So these two definitely put the gradient where let's say equals something.
Okay.
Has some value starting this equation.
I didn't find it yet, but I feel that something must.
Yeah, because
We were looking in the
I
general
mean,
case, yeah, so
if
maybe
you
this
call
case,
it-
yes.
If you're calling it a Hamilton equation, that's not this one. The equation obviously is, we could call it a kinetic equation. but I don't think.
Yes, you have to check the control literature.
Yes.
I'm not sure. I mean, I've never seen
I mean,
it.
not-
Yeah,
Maybe you have to go check.
Well, I had a look around and then I thought maybe I was using the wrong keywords.
So did you look at the pseudo chapter and those people?
So those I have looked at, yeah, but it doesn't.
Okay, yeah, this would be my first guess where I would check it from, but I'm not aware either, sorry.
No, I haven't found anything. So I mean, I
No,
just
if
think-
anybody knows, I'd be very
I mean, you know,
interested. Yeah.
and my question on this equation, like, does it happen like in the standard Hamilton equation that you have caustics? Could you have caustics here? I don't know. I haven't. You know, it makes again X and B. It's not so clear. Okay, so
Thank you.
it's
Yeah.
it's a good problem.
Because you get given derivative with respect to V.
Yes, like for the Burger's equation, when the Hamilton equation, you take the derivative, and you see the Burger's equation, immediately you see that you get caustics here. You get something like the Burger's equation in one variable, but you have the X. So it's not so clear. So it could be interesting to check just basic things in this equation.
I think I said it to what we did something that works for this problem, but I think
No,
yeah,
just
it's
a few
big,
minutes.
yeah.
That means you need something more. Okay. For the equation, we call it caustics because there is a variance. It comes from optica. You know,
Is that
refractive.
refractive?
It comes from where, from the application of optics. That's why they call it
The
caustics.
reason why she gets approved without the regularity, the average lemma. That's the reason to use the average lemma.
No. This is the good tool of going again to some average. It's a singularity.
It's refractive rate.
Yes, if you just take the standard Hamilton Jacobian and you take the derivative, you get Burgers.
It's a trivial question. I don't know why it was funny.
You can ask me a mechanical.
Yeah. People want to have their cake.
No, easy. Yeah.
You're assuming for.
Okay, nice.
Yeah,
Remember one?
Thank you very much.